research, econometric games and economic behavior, etc. in this topic. He wrote at least 2 handbook chapters on related topics, and he has very nice results on it, and he's served as serving as a member of editorial boards of for example, the International Journal of Game Theory, and so on. So that's all I would like to say. And Bernhard, the screen is yours. Please.
Yeah, so the next, now let me get to the screen, try to do the screen sharing, which I'm now probably failing to do. 1 second. I'm sorry. So we have to, no.
There is at the bottom again, there is a share screen.
Very good. Share screen. Thank you.
And you can do.
This is desktop 2, probably. Do we have the screen now?
Yeah.
Perfect. Okay, so this is my, so many thanks. It's very nice to speak to a global audience. 89 people here, very good. And I will talk here on joint work with Baral Atsul, Yugal Garg, Ruta Mehta, and Melin Sohoni. The people involved, Yugal and Ruta, I have met in person, the others not yet. I don't think the others are on, but as listeners, but maybe, anyhow, this is my co-author. So I will talk about a special class of games, Rank-1 Bimatrix games, and they will share a lot of features of zero-sum games, but be a lot more flexible economically. So let's look at Bimatrix games first. I mean, here is a game where we have 2 rows, 2 columns, payoffs, the identity matrix for player 1, 1, 0, 0, 1. The red ones are the red payoffs are for player 1, the row player, and the blue payoffs are for the player 2. And if you mark the, so these are the 2 matrices that define this game. And if we mark the payoffs with boxes when they are best responses, we see 2 pure equilibria here, and in fact, also a mixed equilibrium. And the way, so the mixed equilibrium plays probabilities 1/4, 3/4 for the rows, and a half for the columns. And we know they already exist by Nash theorem. And here is the geometric way of finding them, which is, let's look here at this first diagram here. We plot the expected payoffs to player 1, say, when you play either on the left or on the right. When you play the left column, you get 1 and 0, which is this payoff here, 1 and 0. And you play the right column, you get payoffs 0 and 1 here. And this line here describes the expected payoff when you play anywhere with a probability in between. So this is the expected payoff for playing the top row.
I don't see the figures.
You don't see the figures?
No, I see only the matrix. I'm still stuck in the first page there.
Yeah, that's the same for me too.
Okay, sorry, is it not, so you don't get a full screen here?
We do, but we see,
no.
we
see
see
only the first slide.
We cannot see screens. We can see only applications. For example, your Acrobat Reader or whatever.
Okay, so maybe...
Okay. So you have to change the active window in order to see what you would like to show.
Okay, I see. Maybe so let me stop the sharing. Let's try it again. And maybe this one.
Yes.
Yes. Yes, that was good.
Yeah.
Sorry about this. So apparently, do you see the -2 at the bottom or not?
Yes.
So there is do you see in the bottom right corner there's a 2, and then there's a -2 of this. Do you see that?
Yeah, we can see that.
Yeah.
Because it has a funny frame here, which is not the same. Okay, anyhow, so you see my cursor here at the bottom. Anyhow, sorry, so to repeat, we plot the expected payoff. You see it now, the figure?
Yes.
In the middle. Okay, for top row and bottom row as a function of the probability of playing the right strategy. And the upper envelope of these expected payoffs tells you what player 1 would play. So player 1 would play top if the probability is less than or equal to a half, bottom anything above that, and either one when they are equal. And when you do the same thing for the payoffs for player 2, you get an expected payoff that goes from 1 to -1 for the left column, which is this line here, or for -2 to 0, which is this line up here. And again, the upper envelope is what you have here. And thereby you identify the equilibria, for instance, top left, bottom right, but also the mixed equilibrium where you make the other player indifferent here. So this is the typical way of plotting expected payoffs and identifying possible equilibrium strategies. Okay, so what I want to do now is look at questions about algorithms. There's a general algorithmic problem here. When you have an m by n Bimatrix game as an input, and you can ask what are its equilibria, or you can ask whether it's just one equilibrium, which is a simpler question. And in fact, for small games, say where we have no more than 3 strategies per player, we can actually do this upper envelope story, which is a polyhedron that we can enumerate the vertices of and try to match them to check whether they're equilibria. But they are exponential in numbers, so this is infeasible when m and n become larger. And in fact, already the decision problem whether one equilibrium is, there's only one equilibrium of the game, or more than one. This is an NP-hard problem. You can clearly verify that there's a second equilibrium, but not necessarily that it's unique. And there has been a whole complexity class called PPAD, which finds one Nash equilibrium by path following. And it has been proved that Bimatrix games are PPAD complete. But for this class, although in practice this path following works quite well, I've tested this and it works easily for up to 1,000 strategies per play. Okay, so what I want to now look at, and this is the theme of this talk, we'll look at parameterized games. And here I give a little example that starts again with the identity matrix for player 1 and the very simple matrix 0, 0, 0, 1 for player 2. But to the second column, I will add a parameter lambda. And so, for example, if lambda is equal to a half, the payoff matrix for player 2 is 0, 0 in the first column and a half, 3 halves. In the right column, obviously, this is a dominated strategy. And we can also see the upper envelope diagram, which has a constant 0. We'll always have that here at the bottom row for the left column. And now the right column goes from a half to 3 over 2. So right will be played. That means we have probability 1 for right, and then B is the best response. So we are here on the right. So we get this green equilibrium here. And now I will look at the equilibrium as a function, or the equilibria as a function of lambda. Suppose we lower lambda to 0. At that moment, a second equilibrium component in fact will pop up, which means you can also play the left column now, which is the best response, if you play only the top row. Okay, if you play only the top row, these are both best responses. And in fact, the top row stays the best response if you mix anywhere between 0 and a half for left and right. So this is the second equilibrium component, a degenerate game. If lambda now becomes a little smaller, again, we actually have 3 equilibria, which you see from these intersections. And when lambda becomes -1, okay, so this moves the probability of the mixed strategy shifts as a function of lambda here. And when lambda is -1, we get another equilibrium popping up here, a whole degenerate one, and then only the left one remains. Okay, so this is following the equilibria as a function of lambda. And what is quite interesting, what you don't see here from the picture, you've seen how the equilibria came about, but what it in fact happens is that the equilibria have a very special structure. Namely, here's a new diagram which says what are the equilibria as a function of lambda. Left is the game. And here we have the probabilities for right and bottom, which are the 2 strategy sets. And in fact, lambda, when you go down here, it's actually a path of equilibria that results here. Here you see how it is. So it's not popping in and out. It's actually having a very nice path following structure. And to give an example, when lambda was 0, we cut across here and we get the equilibrium component here for player, this one here, the rectangle, and the other equilibrium, which is the triangle. Okay, so this is how to read this diagram. As a function of lambda, you cut across and you get the different equilibria. As long as lambda is between -1 and 0, you have typically 3 equilibria, except at the endpoints where you have these components. Okay, so this is the path following method when you parameterize the game with the linear parameter in this case. One second. And now it turns out that this is actually something that has been observed before by Govindan and Wilson, which they call the global Newton method, which works as follows. For a two-player game, you can do it in general. You have an n by n game A and B. And now let's look at the vector of bonuses for the rows, say C1, C2, Cm, which we add to the row. Okay. And similarly, you have a vector B of components of bonuses that you add to the columns B1, B1, 2 up to Bn. And there's now one extra feature here. You scale the whole thing by lambda. So when you write this in vector notation, it's column vector C, scalar L, row vector of all ones here. And here's the other way around, column vector of ones, lambda B transpose. That's where the lambda belongs. And I've written it out here like this. And now it turns out you can see what happens when you make lambda very large. Let's suppose B has a unique maximum for simplicity. So then clearly that maximum dominates this term here on the right when lambda is very large. So this will be the unique pure strategy J, say Bj is the maximum that you play, and then you play the best response to J in the rows. And thereby you have a pure equilibrium to start with. And when you then lower lambda, it will turn out that you change the game, but you can follow the equilibria that you do, I mean, along a path. And you can even implement that by a complementary pivoting method, which is similar to the simplex algorithm called Lemke's algorithm. And you can follow this path until lambda becomes 0, and that will then solve you the game. So that's the global Newton method. Okay, so this is a known method when you look at parameterized games, linearly parameterized by lambda. Okay, and now, oh, and by the way, I mean, if this bonus vector here has 0 everywhere except for 1, where you have a single 1 in there, so it's a unit vector, this is actually also another version. In fact, it is the famous Lemke-Hausen algorithm for finding one equilibrium. Okay, so what we do now is we use this lambda in a different way. And for that, we look at the following. Let's just recall in zero-sum games, we have unique equilibria. Here's an example of a zero-sum game, a kind of matching panics game. And we will come back to that, but it's a convex set, and it's also a solution to a linear program, which I will refer to later. So what we now do is we generalize the concept of zero-sum games. And we do this as follows. This is called the rank of a game, and this is the matrix rank of the sum of the two payoff matrices. So clearly, when we have the all zero matrix in a zero-sum game, this is a game of rank 0. But this is a hierarchy of games. So we have games of rank 1, rank 2, and so on. And the question is, are they possibly related to zero-sum games? Are they solvable in some way, and so on? So these games were introduced by Cannon and Theobald, and they proved that an approximate equilibrium of a fixed rank game can be found in polynomial time. Let's understand what that means. Fixed rank means that you increase the size of the games, but you keep the rank constant. Okay, and then as a function of the size of the game, the running time is polynomial. That's what always complexity is about. You look at running time as a function of the input size. Now, the paper that we are extending here in this paper started with doc 2011 by my co-authors, which said that an exact Nash equilibrium of a rank 1 game can be found in polynomial time. Before we had only approximate equilibria, now this is an exact equilibrium. Okay, so the main story about rank is the following. When you have a matrix of rank k, then you can represent it as a sum of rank 1 matrices. So a rank 1 matrix is a column vector times a row vector. And if you have k of these rank 1 matrices and sum them up, then you can write the matrix in this form. By the way, this is a nice way you can derive this from the, say, the column rank of the matrix, but this is a symmetric condition in the rows as well. So this is an easy consequence that row rank equals column rank from that statement. I say at most k, I mean, if these rank matrices are, so this is a matrix of at most rank k, it could be lower. But if it has rank k, we need these k summations. Okay, and now this in particular implies that we can write a rank k game if k is at least 1, as a game of rank k minus 1, AC, plus a rank 1 matrix AB transposed. And if the game itself is of rank 1, that means then this is of rank 0. So we have here A and minus A plus AB transposed. Just double checking, there is still some white space below the game of rank 1 for you?
Yes.
Yes, yes,
Yeah,
good, good,
yeah,
good.
yeah.
Because as I say, my screen looks funny. Okay, now, an observation that thrilled me when I found it was the following. I mean, you will see the consequence in a second. Here we have a game of certain rank, and we have, so we write it as A and C plus AB transposed. And now I do the following. I discard the A here, and instead I look at the vector B as a vector of column bonuses, which means I have constant columns here scaled by lambda scaled by B, which is the kind of thing I was looking at the very beginning. So I give a column bonus, B1 up to Bn, scaled with lambda to each column. And the A appears now on the right-hand side, which says that the A vector here that I used here times the vector, times the probability distribution X is equal to lambda. So this is a claim that says I can write xy, if it's an equilibrium, as an equilibrium of this parameterized game, and this hyperplane condition, x times a is equal to lambda. And that's a thing worth proving because it's very short. So clearly the two games here have the same payoff matrix A, so the row payoffs are unchanged. So clearly x stays the best response to y. So let's look at the column payoffs. If x transposed A is equal to lambda, as we state here, then the column payoffs for the first matrix can be written as x times C plus AB, which is this here, x times C plus, now this is XAB transposed, which was lambda. So the lambda is here. And now I put the x transpose 1 here because this is a probability distribution. So x times the 1 vector is 1. So I can take it out again. So this is x times C times 1 lambda B transpose. So that's a very simple proof of this equivalence. Straightforward, just a bit of algebra. So in a sense, I have replaced here the lambda with the average column payoff here. And that's what I use here all the time, the lambda. Okay. Now, one more thing. What we have done here is we have added a constant to each column. And what I do now is I subtract the same constant from each column of the row payoff matrix, which we know doesn't change the equilibria, because anything that is the best response against y for A stays the best response against this one, because I simply subtract the constant column times the probability of playing that column, but it doesn't affect whether I prefer one row over the other. So what I have here is a matrix where I have A minus some constant columns, C plus some constant columns, and they cancel out when I add them. So you have here A plus C. So this is a game of one game rank lower. So I have now represented the equilibrium of this game with the equilibrium of a lower rank game plus this intersection with a hyperplane. Okay, so I have a rank reduction. Okay. So let's look at what this would mean in an example. So here is a game where you have A, the identity matrix, B is this matrix. When you sum the two up, you get 2 minus 1, 1. So this is a rank 1 game. Yeah, because this is minus A plus this rank 1 matrix. Why? Because it's the vector 2 minus 1 times the vector 1 minus 1. These are multiples of each other, these rows and columns. Okay, and now I look at this parameterized game. Remember, that's what we were doing. Instead of looking at this game, we parameterize now with a constant vector 1 lambda times B, and we get these lines that represent the equilibria as a function of lambda. And so this is the equilibrium set parameterized by lambda of this parameterized game. And now I intersect it with the hyperplane, which says x times A is lambda. So x is a probability distribution. So this is a convex combination of 2 and minus 1. So when x is 0, so x is 1, 0, we have 2 here. If it's 0, 1, we have -1, so it goes from 2 to -1 lambda. And this black line here on the right intersected with this curve, this thing are exactly the 3 equilibria of the original game. This is a game with 3 equilibria and not just, I mean, so it has 3 equilibria. So this is an example of how this works. And now we come to the main story. Namely, we can find one such equilibrium by a suitable binary search for lambda. And what I do is here, I start with a value for lambda that is, I'm sure, is bigger than any x times a. So it's something which is bigger than 2. And also another lambda, call it lambda lower bar, which is lower than -1. I don't want to start exactly with 2 or -1 because then the search would immediately stop. I want to have something slightly more interesting. So I look at this search interval between -1 and 2.5. So this is this blue line is the search interval for lambda. And I have some equilibrium here. I know there's an equilibrium which has the value greater than lambda. So there's x lower bar is one equilibrium strategy that is greater than lambda lower bar, and this is less than that. This is an invariant I maintain. And now, as in any binary search, I now look at the middle value of the 2, which is simply this thing. Okay? And now we see this is below the hyperplane here, the black thing. So we have the inequality greater than here. And so we make that now, we move up the lower bar. So we have cut the interval in half, and we still have the one equilibrium above, one below, and the curve here will intersect the hyperplane, and therefore we know there will be a search that will eventually succeed. So let's look at the next half point, which is this one. And again, it's below the hyperplane, and so we can move that up. And now we have a second piece of information which you can identify combinatorially if you solve these equations. Namely, it happens to be the case that these 2 equilibria are on the same line segment of the path. It's in a sense the same linear programming variables that you use. And now you can solve them directly. You don't need to continue the binary search. You can effectively directly solve the equation that you want because they're under the same path segment. It's a piecewise linear path, and then you find the equilibrium. So once the path segment has been reached that they lie on, we can terminate and solve the game. So we have solved now the binary search for the search problem. Okay. Now, this is great. And what I thought was we can do this in our general rank reduction, which would be cool. And that would be as follows. We start with, so we want to find lambda and xy to the lower ranked game such that x times a is lambda. So we can start with, say, the maximum of the a entries +1, minimum -1, as I did before, and then do the following search. We cut the lower and upper lambda in half, take the midpoint. This should be actually probably a +1, plus here. And then we find an equilibrium that corresponds to the lambda, and depending on whether we have less than xa or greater than xa, we take the lambda lower bar or upper bar as the current value of lambda and maintain this invariant until they're on the same path segment, and then I can solve them directly. Now, the question is, does this work for higher rank? Which would be cool, because then we could do successive rank reductions to solve any game, to find one equilibrium recursively. I mean, at least with constant rank, that could be a polynomial time algorithm. And the following example shows you that this is not the case. Namely, so let's look at an example. It's a curve that you've seen before. Let's look some different a. Say we look at a hyperplane that has this point and this point, and this actually intersects this graph here actually in a single point. So there's a unique equilibrium to this game. And now we do our binary search. We start with a high value here and a low value, and this is our search interval. We take the midpoint, and this is above the hyperplane, and so we are here. And now let's cut it in half again, and now we are now here. And now we have multiple choices. Suppose we choose this equilibrium here, this triangle. So we are below. And we make now this the search interval going from here to here. And then we keep searching. And as it turns out, we actually have lost the game already at this point here. Why? Because the lambda that we're looking for is this one here, the purple one, which is down here, but the lambda, the search that we are doing has actually left already, the search interval has already left the lambda. So we will converge. We'll converge in lambdas, but we will not converge in the x's, and we will not find the equilibrium. And the reason when you sort of take away, the path, is that what we have created is here a disconnected path, because the path is here, and we intersect it like here. It has multiple components, and therefore it can become disconnected. And so we can search as long as we want, because we will not find an intersection of this graph with the hyperplane anymore. So the question is, what went wrong? What went wrong is exactly that the lower rank game has disconnected equilibria. And this is exactly what cannot happen when the lower rank game is a zero-sum game, because a zero-sum game will always have convex equilibrium sets. So we cut across here, like we did in the previous example, where this was a zero-sum game. Remember that this parameterized game is strategically equivalent to a zero-sum game by subtracting these constants here, payoffs. So when we cut across, we always get a zero-sum game solution, which is a convex set. Even here, it's a convex set where we have these steps here. And for that reason, the path must be monotone, because if it was not monotone, it was turning back, we would get disconnected sets, which cannot happen in a zero-sum game. So for rank 1 game, this parameterized set of games, at its equilibria, is actually a monotone path, which is essential for the binary search to work. Okay, so the binary search does work if the original game has rank 1. And in fact, in polynomial time, as we proved, there's a bit of, it's straightforward actually. And in fact, in retrospect, it would have been too good to be true if this had been true for games of arbitrary game rank, because Ruta, my co-author, proved already that rank 3 Bimatrix games are PPAD hard. So you would have found a polynomial time algorithm for rank 3 games, and together with PPA hardness games, that would have been a sensational result, unlikely to be true. In fact, Xi Chen and Orfani Paparos and Yanakakis, maybe she is listening, he said he might. Xi Chen said, I don't have seen the paper yet, but they said they have already found the proof for also rank 2 games. So in fact, already at rank 2, we have PPAD hardness. Rank 1 is what we can do. Okay, so let's now focus our attention on the rank 1 games. Okay, so let's recall what we did here. A Nash equilibrium of such a rank 1 game here is actually a Nash equilibrium of the parameterized game, where you add certain lambdas, b's to the columns, and the hyperplane that says x times a is equal to lambda. And we knew in this previous lemma that we could subtract these same constants from the payoffs of the role player, and thereby now create a zero-sum game here. So we have the Nash equilibrium of zero-sum games and this hyperplane. Now a parameterized zero-sum game like this is actually, in a certain sense, can be described by a parameterized LP, which I now want to look at, a linear program. And for that, we look at, first of all, a general linear program, a linear general zero-sum game. So in this case, lambda is equal to 0. So a and minus a, this is our zero-sum game. Now, equilibrium is a min-max strategy, which means the following. If I look at all possible mixed strategies y, so this is described by the following linear constraints. The sum of the components y, this is the all 1 vector times y is equal to 1. So they sum up to 1, they are non-negative. So this means this is a probability distribution. And among all these probability distributions, I now try to minimize the payoff u that I have to pay in every row. So that means every row, this is a times y is the expected payoff in each row to player 1. And player 2 is the minimizer. Yeah, this is -1, these are her payoffs. So she tries to minimize the u that she has to pay for each row. And if you solve this LLP here, you get actually a min-max strategy. And it turns out that the dual solution x plus the corresponding payoff that corresponds to this constraint here is actually the max-min strategy for the role player. So linear programming duality is actually a proof of the min-max theorem from Neumann. Okay, so this is well known. And what I do now is I will look at this LP. I will simplify it a little bit by writing y in y for these two constraints. This y is now the mixed strategy set where y sums to 1 and is now negative. This means the constraints for y. Okay, and now we go to our parameterized game, because that's what we're interested in, where the payoff matrix to player one is A minus 1 times lambda times B transpose. So I now have a LP where I parameterize the payoff, the entries, the matrix A of the LP. Now, I changed that a little because I will now do a little substitution that simplifies the story by writing this right inside U as the linear expression, a scalar T minus lambda B transposed Y. So if I do that, then I have on the right hand side 1 times 1 minus 1 times lambda B transposed Y. So that cancels. So this thing becomes now minimize T minus lambda B transposed Y, subject to now a much, much simpler constraint, namely AY less than or equal 1 times T. So this was exactly the original upper envelope of payoffs to player 1 when you play Y, which you try to minimize. The best thing that could happen here to player 1. And so this is a constant polyhedron. And the only parameterized story here is the lambda is the objective function, T times, so there's a term T in T here, which is here, and it affects the Y. And so all we have done here is a parameterized LP where lambda is parameterizing the objective function. Well, this is a very, very typical parameterized LP that has been studied for a long, long, long time, namely, I think 1955, Garth and Sati, where you parameterize the objective function and try to look at how the solutions of the LP behave as a function of this parameter. Very standard object. Let me explain a little bit this transformation. Here I have, so for instance, in our example where B was minus 1 and 1, so these bonuses were minus 1 or minus 2 and 2, something like this. I think minus 2 and 2. No, minus 1. Never mind. Anyhow, this would shift the endpoints of these upper envelopes. Here like this, if I have minus 1, so this would be a plus 1 here, minus 1 here. Here's the one with 0 in the middle. And you see the minimum of this over Y. This is the max-min strategy and corresponding payoff. You see this is this green thing. And this is when you twiddle with the matrix. And here is the next picture showing the same thing with the objective function, where you keep this constant, but you now turn the objective function around. So this is a direction of the objective function as a function of lambda. Depending on where lambda is, it's a hyperplane that is either here or here or here. That's the objective function. You see it has exactly the same optima here, 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 or here. Okay, so this is this equivalence. You keep the polyhedron fixed of constraints. You only vary the objective function. And you can see a little bit geometrically what's going on. Imagine this is this polyhedron that we have. We have this hyperplane pointing in a certain direction, and now I change the direction, which you can think of like wrapping around this hyperplane, rolling around this polyhedron. It's only the lower end of the polyhedron. It's its effect. So, yeah, this is what we're interested in. And so you see this is either a vertex or edge of the polytope generically, and that's why it defines a path. It's a piecewise linear path. It could be in the general cases also have higher dimensional faces here. But anyhow, we're wrapping this around, and this is exactly how a geometric view of parameterized linear programs. And let me also say one more thing about this. This is also known because essentially we are having only 2 dimensions here for this wrapping, because we have lambda is a single, so you have one vector, which is t, 0, and the other vector is 0, b times y, or 0 and b times lambda. So we have only 2 vectors of objective function. It's a real plane, a 2-dimensional plane, and you can think of this path as projecting the polyhedron of constraints to this 2-dimensional plane. And this algorithm has also the name of shadow vertex algorithm, which you might have heard. I mean, and yeah, I'll say something about a little bit later, because this shadow vertex algorithm is also polynomial. It has a lot to do with what is called smooth complexity. I'll mention it. Okay. So now we do have here this binary search algorithm for find and one equilibrium for a rank 1 game, which says the following. And now the paper that we wrote, it's already, it should be out soon in operations research. Is going very much in detail into this. I mean, we look at these parameterized, this is the parameterized LP that we look at. As I say, it has been very well studied. And so this generates a sequence, a path, or if it's a generic game, or a sequence of faces in a general case, I would still call it a path on this polyhedron as a function of y. And we want to have an intersection of this object, this path, with a hyperplane x lambda, where x transpose A is equal to lambda. For that purpose, it actually is useful to look at the dual LP here, because that involves the x rather than the y. And now you can do either binary search, this is my algorithm 1, and then find the solution in polynomial time, and thus one equilibrium. Or you can do another thing, you can follow the path by pivoting along it, which is what is done when you solve parameterized LP. And whenever you intersect the hyperplane, you have found an equilibrium. And at that point, you can either, it's a single equilibrium, a single point, or you can enumerate the entire phase that you found. If it's a degenerate game, it has a phase of equilibria of this polytope. So what you do is, unlike in the Govindan-Wilson algorithm, where you drive lambda down to 0, what you do here is you have this extra constraint, depending on the current sign of x times a and lambda. You have the constraint that you have either greater than or less than or equal to lambda. And as soon as either of these constraints becomes equality, which is a pivoting step, a binding variable that you encounter, that gives you an equilibrium. So we have here different values of lambda that give you different equilibria. And the beautiful thing about this thing is you follow a single path and you scoop up all the equilibria. Remember that when you have, so this is the nice thing about this algorithm, you find all equilibria of the rank 1 game, whereas in a general Bimatrix game, like Govindan-Wilson, path following finds you only one equilibrium. So we're doing a lot more by following a path. And now let me say this, if you have a slightly perturbed game, which is called smooth complexity, this path should actually have only polynomially many segments, okay? So in fact, for a slightly perturbed, if it's not a very special game, it will normally have also only a polynomial number of equilibrium components. Okay, so this raises the next question is, how many equilibria could I have in a rank 1 game? Maybe the fact that we can find a rank 1, a single one in polynomial time, maybe can find all of them in polynomial time. Are these perhaps less complex questions, complex games? And this is a question that Kanan and Theobald asked. For instance, they could have polynomially many. And this turns out to be equivalent to the question, as you've seen, how many times can the path of solutions to a parameterized linear program intersect a hyperplane? Okay. Now this question has an answer that has been answered for a while. It turns out this can be exponential. And there's a paper by Murty from 40 years ago now, which looks at the following parameterized game. Actually, it's a dual. So we parameterize the right-hand side rather than the objective function. The objective function, so the matrix is very simple. It's a lower triangular matrix, which has 1s on the diagonal, 2s on the below the diagonals and 0s above. And then it has these exponential right-hand sides, -1, -2, -4, -8, plus lambda. And exponential weights for the Z0, Z1, Z2, Z3, 1, 4, 16, 64. You see how this goes on. And it turns out that if you now pivot by wrapping around our hyperplane and lambda goes here from 0 to 16, it turns out that you wrap around a kind of cube by encountering, like the gray code, every single vertex of the cube. So you get exponentially, it's a kind of fractal path that you generate that way. And this allows you to, so it's exponentially many linear pieces. 2 to the dimension. Here dimension is 4, so 16 pieces. And so you can construct actually with some trick. I mean, you can boost up these spikes and then find a suitable hyperplane, and in this case get an intersection like this, which has 2 plus, getting a bit hoarse. Sorry, I need to, never mind, I thought I had a lozenge. Anyhow, you get here 9 Equilibria. This is straightforward for Murty, and it turned out that that you can do from this construction. And then I found by, inspired by his work, and I still haven't found exactly how I found it, but a game which actually has even 2 to the n-1 Equilibria. So in a 4x4 game, it would have 15, not just 9 Equilibria. So here's the construction. I take a number, say 4 or 3, bigger than 2. Doesn't have to be an integer as long as it's bigger than 2. And now I do the following. It's an upper triangular matrix. So I have zeros below the diagonal, something times 1, which is this 0, p to the 0, p to the square, p to the 4, and so on the diagonal. And everywhere else, it's 2 times the sum of the row and columns if they start at 0. So for instance, here in row 0, p to the 1, p to the 2, and so on. But here multiplied by 2. And it's a symmetric game. I take A to be equal to B transposed. So B transposed is now this one. And now if you add them up together, you realize that you have in each row and column ij 2 times p, this entry here, p 2 times p to the I plus j. So what is that? That is 2 times p to the I times p to the j. It's a multiplicative structure. It's a rank 1 matrix. Okay, so A plus B is a rank 1 matrix. And what I'm now showing you is that this has, for every possible subset of strategies, an equilibrium that has this subset as a support on both sides. For example, the set of all strategies. Let's start with that. Let's do this with an example. So let's here say, suppose it's a 3x3 game. P is 3, so the matrix looks like this. 0 is below the diagonal, 1, 9, 81 on the diagonal, and multiplied by 3 times 2. So 6, 18. This is the matrix. Okay. And I construct now the fully mixed equilibrium as follows. I go here. I give a weight 1 to the rightmost. I start at the bottom. 1 times 81 is 81. Now 1 times 54 is less than 81, so I can add something, make a bigger value. So I equate these 2 columns to also create 81. And then again, this row again has lower weight. And this works because p is bigger than 2. So that's why this works. And then here I have need an even higher weight. And then I have now given weights 1, 3, and 45 to the columns, such that each row has equal payoff. Well, I need to divide by the sum in order to make this a probability distribution. So I've here created a fully mixed equilibrium. But the same story can be done with any game. So for example, say the support is only the first and last row and column. I start the same, 81, bottom row. Now I don't use this column, so there's lower payoff. And then I need a bigger number here, obviously. 63 plus 81 is, plus 18 is 81. And again, I renormalize, and now I get the first and the last row column as exactly the kind of strategies that are best responses, the pure strategies against these payoffs. Okay, so this is another equilibrium, and I can do this with any subset, non-empty subset, and therefore I get 2 to the n-1 equilibria because there are 2 to the n-1 non-empty subsets of the S supports for the rows and columns. Okay. And this raises then now, so this is an example of an exponential output that I could have. So obviously I cannot expect to output all equilibria in polynomial time if there are exponentially many of them, because I mean, that's unfair. I mean, I have exponentially many of them, I need exponential time. So a new complexity notion is output efficiency, which says polynomial time in the size of input and output. In other words, polynomial time for each single equilibrium. And my conjecture is, this is still a conjecture, that this is probably not the case, because the binary search doesn't give you any information. So here's the story. What I conjecture is the following. I think, but I'm not there yet, I conjecture that if you have a rank 1 game, that there is the decision problem whether there's an additional equilibrium, which you can easily verify by giving it that this is actually NP complete. Or to put it another way, uniqueness is co-NP complete, but this is what it means. I mean, you can verify that there's a second equilibrium, but you cannot verify easily that this is the only equilibrium because of this exponential nature. And if that is true, so as I say, I'm still working on that, then we would have something very interesting, because so far people understood difficulty of a game in terms of the classical NP hardness notions, because that was the complexity notions that people knew. So if that is true, what I say, then we would have here an example of a game where I can find one Nash equilibrium in polynomial time, and I can even have exponentially many equilibria, and yet I can find one polynomial time. But the decision whether it's unique is co-NP hard, which is true in general games. So that would mean that the PPAD hardness, which clearly doesn't apply here, because, or probably not, because I can find the equilibrium polynomial time, that this is a very different notion to the uniqueness problem that gives rise to these decision problems. Okay, so we have here this rank hierarchy, zero-sum game, everything is fine. Rank 1 is what we're doing here. And I think, as I say, the uniqueness is already NP hard, co-NP hard, and here already we have PPAD hardness. And by the way, the approximation story doesn't give you much. It's very bad in terms of the rank and also the epsilon that you want to approximate it for. Okay, so let me ask some, we have 10 minutes, is that right? Something like that left? Okay, so let me raise a little bit of open problems and then go to one thing that I mentioned in the abstract afterwards. So in summary, so far what we have seen here, they can be solved really fast in the following sense. You can find one equilibrium in polynomial time, and you can scoop up all of them with a pivoting algorithm that is related to finding one equilibrium in a general game. So if you have that, I mean, now I'm a mathematician who has a good hammer, and it can find suitable nails for it. And it suggests that if you have really large games, maybe there should be rank 1, because then we can solve them fast. So it would be good. I think it's an interesting challenge to find applications of rank 1 games. And this raises the question as, do these rank 1 games have an economic interpretation? So for example, if you look at a Cournot game, a classical, you have quantities, non-negative x, y. This is the quantity you produce. This is the price you can get, 1 minus x minus y. This is a rank 1 game because you can add some constants. So if you discretize it, it's a rank 1 game because you can add some constants to the row, to the columns of the row player, to the columns of the column player. And if you add this up, you are remaining with the x times y rank 1 component. But this is a game with unique equilibrium. You don't need an algorithm. So maybe here's a suggestion for an economic game that has rank 1. And if you have any comments on that, that would be very helpful. So suppose we have a role player who can sell a product which can have certain levels of quality, I 1 up to m. And the buyer can buy certain quantities 1 up to n. Say these are AI and BJ are the corresponding entries. And now I assume that there's a price. We know that there's a price to be paid. This is a completely zero-sum component. Pij is paid from the buyer to the seller. So this is a payoff to the seller, the loss to the buyer, but they have a benefit from trade. Say this is AY times BJ. Well, higher quality will cost something to produce, but you gain something for it. And if you sum these two things up, in fact, you can have some constants that don't matter depending on the rows and columns for the two players. You get a rank 1 game where if B is bigger than beta is bigger than alpha, you have the benefits from trade here. So this is, I think, a very reasonable rank 1 game. And the beauty of this is that you can play with these prices. If this is Netflix selling or Amazon selling its stuff, maybe you can play a lot with these prices because that doesn't affect the rank 1 prediction and then interpret the game and try to find out what prices work well. The only question is, I mean, whether these mixed equilibria that I find make much sense. I mean, that's the question. Okay, so let me conclude with one extra mathematical observation that we also have in our paper, which has to do with these paths. Namely, there is a famous structure theorem by Kohlberg and Mertens that says the following. It's an amazing theorem. I stated here with 2 players. So you fix the dimension of the game. It's true for any number of players. So this is an n by n game. And it says the following. The equilibrium correspondence of the Nash equilibria for these games is homeomorphic to the very flat space of games. So what is the space here? It's the thing where you parameterize it with all the payoffs. So it's 2 times m times n many payoffs. And such a game here in this space can be actually mapped 1-to-1 to a game and its equilibrium. So this is kind of the equilibrium manifold, if you wish, which is kind of like a blanket layered over this space. So to give you a glimpse, we have done something like this by looking at here. This is an element of a line in the strategy space. So this is a specific game. We have a line in this Euclidean space of all possible games that follow lambda. And if I look at the equilibria, it's also kind of line. It's this path that we looked at. So this is kind of a cross-section, a slice through this equilibrium correspondence, which is in general this blanket. And this homeomorphism was introduced by Kohlberg and Mertens in order to study stability. For instance, in this game, if lambda is 0, this is a non-stable component here, because if you wiggle lambda a little bit up here, it disappears. But here's a stable equilibrium. And that's exactly what they proved with the help of this correspondence, strategic stability. That's what they were doing. Okay, and now comes my story. This homeomorphism does not preserve the sum of the 2 games. In particular, it does not preserve the zero-sum property, for example, and this is something we can fix. And let me spend a little bit of time now, 5 minutes, in explaining the correspondence by Kohlberg and Mertens itself, which has a proof that everybody should know because it's much simpler than people think. And so I give this proof first, and then I also give the statement and a little bit of an idea of my proof for the new, so we'll have a new structure theorem. That's what it's about. Okay, so what is the trick of the classical Kohlberg-Mertens homeomorphism? The idea is that you parameterize games in a new way, in the following way, that the only thing that you vary is a single m vector for the row player and n vector for the column vector. These are the number of rows, number of columns. In the following way, this is a vector of bonuses for the rows times a constant row here, plus a base game, I call it a tilde, which has the feature that the average across all rows is 0. So let's look at an example. This is A, which has 0, 8, 4, 6, 6, 0. So the row average is 4, 5, and 3, which you take out here, a constant. This is the A, 4, 5, 3, 4, 4, 5, 5, 3, 3. And now this is a game. This is the alpha tilde, where the sum across rows is 0. Okay? This is unique and very simple decomposition of A. Let's do the same thing for an B. Here we do now constant columns in this game, which has the payoffs 4, -1, and so on. Constant columns here, creating a game where the sum across columns, 8 plus 3 minus 11 is 0, 6 plus 6 minus 12 is 0. Okay, so this is a unique decomposition. And now I only look at this A and the B, which we have here. And we now can define very, very, very simply the homeomorphism by going from an equilibrium to a new game. It's the right arrow that we're now describing. Namely, all I do is I take A times Y. So you have an equilibrium here. So this is the payoff of expected payoffs, the vector of expected payoffs, A times Y, to which we add X as the new parameter. And similarly, this is the new parameter for the other player, same base game. So the only thing that we manipulate is this vector here, 4, 5, 3, -4, -6. Let's look at our example again. Here we have one equilibrium. This is a game that has 3 equilibria. If you play 3/4, 1/4 for the columns and 0, 3/4, 1/4 for the rows, The columns payoffs are 2, 4.5, 4.5. Okay, so you see 1/4 times 8 is 2, and 3/4 of 6 is 4.5, and 3 plus 1/4 of 6 is also 4.5. So these are the two best responses. They have constant payoff because they're maximum. The player must be indifferent between the things that he plays. And if I add them up, I get now the new row parameters, 2, 5.25, 4.25, for this game C. And the cute thing is I can reconstruct, uniquely decompose A and XY in that way by simply, so I think of this as water levels. So these are poles that stick out of the water of certain heights. And now I lower the water until exactly mass 1 sticks out, which then will give me the X. And if I subtract that, I get exactly a best response payoff, Y. And from the Y that I can reconstruct in the same way on the right-hand side, I can actually reconstruct the A, I mean, with the, from the base game. So I can actually go, that's why I can invert this, okay? So it's a beautiful thing. It uses the equilibrium property that X is the best response to Y in just summing these two vectors to create the new parameter here. Absolutely beautiful proof, I think. Okay, so we have this to repeat. I mean, C has the same base game here, but a new parameter obtained from the equilibrium, which I then can use to reconstruct the game of another, I mean, the equilibrium of another game. Okay, and now let's just say what we do. So as I said, the homeomorphism doesn't preserve the sum. In our game, for example, maybe we're interested in it because this happens to be a rank 1 game. You see, oops, my screen is starting to disappear. This is not good. I have to, let me try to, okay. Sorry, it's my screen not cooperating. This is not good. Yeah, I'm sorry, I have to switch the format. I mean, so anyhow, here's the new parameterization, which parameterizes only A. And so the trick is to only parameterize A in the following way, that I get new vectors. So I get a constant here, an A and a B, which have the fact that they're themselves. So I have two parameters which I extract only from A. And so if I do this for this example, it goes as follows. I add a constant, and these parameter vectors A have the feature that they themselves sum up to 0. So this is the vector of row bonuses that I construct this way. So first of all, the matrix itself, and the matrix in each row and each column sums up to 0. So it's a new decomposition, 0, 1, minus 1. And if I keep going doing that, I get this vector 0, 1, minus 1 of row bonuses, of column bonuses, minus 2/3, 2/3, and a new base claim, which I call A hat. And now the trick is that the new homeomorphism does exactly the same trick, but it only manipulates C. So the same gamma, the same base game here, but I say take AY plus X and X times both B plus Y, projected down to the hyperplane that goes to the origin, which allows the exact same reconstruction. And then totally simple, I take D is equal to A plus B minus C. So that's why I trivially preserve the property that A plus B is equal to C plus D. Okay, so this is a new homeomorphism that, for instance, stays within the set of zero-sum games. And that's why, I mean, I find it interesting. And I think I am on time. And thank you very much. So.
Thank you.
I suggest that we all switch on our cameras now. So do you want to still see the screen, or will we go to screen view? I haven't observed the chat, so maybe.
No questions on the chat, but any questions, colleagues?
No question. I really enjoyed the talk, Bernhard.
Okay, so switch on your mic. We can talk. I mean.
I have a question, sorry.
Who was this?
This is Shrira.
Ah, okay. You have a question?
My question is, how easy will it be to these principles to multiple player games greater than 2 players?
Okay, I don't think so. The structure theorem holds for many players.
Okay.
But the rank condition is very much, see, we have the sum of 2 payoff matrices which have a certain rank. And I don't see that generalizable. And it's a very simple games we are looking at. Rank 1, yeah, zero-sum games already with 3 players are not easily tractable at all. They can have irrational equilibria and so on. So from computational perspectives, they are not easy. However, the path following, that also works. The Govindan-Wilson story that I told you at the beginning also works for games with more than 2 players. It's just not a pivoting algorithm anymore. It's a different path.
Okay, thank you.
So,
Bernhard,
yes.
question. I arrived a little later than, so I didn't see the beginning, but let me ask the question. Do you have any duality somewhere here? In zero-sum game, you can have you can use duality to solve the game, and in rank 1, can you use duality also?
So I mean, clearly we have the duality for the parameterized linear zero-sum game. I mean, they have used it all the time by looking at the linear programming and its dual at the same time, because the primal and the dual give the min-max and the max-min strategies for the 2 players. So we use it strongly, but yeah.
For rank 1, you know.
Yeah, I mean, the whole paper that I presented is about rank 1. About rank 2, it's actually negative. We have the nice rank reduction, but we cannot exploit it, which I am sorry about. I was hoping that this could be a much more powerful thing, but it only works for rank 1.
Thank you again, Bernhard. Thank you for the nice talk.
Okay.
Yeah,
well.
glad.
Thanks so much. If you want to hang around, I mean, I'm happy to chat a bit more with friends here. I mean, for my sake, I mean, don't just go away. I mean, that's my. Oh, of course you can go away, but I mean, if you want to say hello, it would be nice to see you. I see a few here. I'm just paging through the 62 people remaining now. See you here. And next speaker is Ehud. Is that you? Oh no, that you in 4 weeks. Is that right?
Yeah. As I said at the beginning, this was not a survey. You can trust me. I'm